The night sky has been telling us secrets for a long time, for thousands of years, and we're going to look at 20 discoveries that changed how we see space. Not just a list of facts, it's more about how our view of the universe gets broken and then put back together, again and again, so by the end you see the shift. From thinking we're at the center of everything, to knowing we're a small part of something vast, something that's accelerating and deeply mysterious. We'll see how we learned the universe had a beginning, that most of it is invisible, and that we might not be alone out here. So which single idea do you think changed our perspective the most? For a long time, the Earth was the center of everything. The sun and the moon and the stars, they all moved around us. This was the old system from Ptolemy. It was more than an idea, it was how the world worked. The universe revolved around the Earth, but by the 1500s that system was having problems. The planets, Mars especially, their paths didn't fit. They didn't move in clean circles. Astronomers kept adding more circles, more adjustments, trying to make it work. The model was getting too complex. Then there was Copernicus. He was a mathematician in Poland. He studied the sky for years. He wasn't trying to start a revolution. He just wanted a simpler answer to the math, and he found one, but it was a difficult idea. He published it in 1543. In his model, the sun was at the center. And the Earth was just another planet. It spun once a day, making the sun seem to move, and it went around the sun once a year. This explained things. The strange loops Mars made, that retrograde motion, that was an illusion. Earth on a faster orbit was passing it. The model was simpler. It fit without all those extra circles. But the meaning of it was hard. If Earth wasn't central, then humanity wasn't the center of creation. Copernicus knew it was dangerous. He waited years to publish. They say he only saw the book when he was dying. It didn't change things right away. The book was technical, but it planted a seed. It said the truth might not be what we see. We have to trust the observations even when they turn everything upside down. That was the first crack. The Earth was moved from the center. Galileo's telescope would prove it later. But the shift had already happened. The universe became something we could measure from the outside. Not a mystery we sat inside. It was more than science. It was a kind of humility. If we weren't at the center of our own solar system, what else were we wrong about? And the answer, it turned out, was almost everything. Copernicus had put the sun in the center. But the orbits themselves, they still weren't right. The planets didn't move in perfect circles. The actual data, the positions of the planets, they just wouldn't fit that ancient, beautiful idea. It took a mathematician, someone with a kind of mystical belief, and the most precise observations anyone had ever made, to finally see what was really happening. That was Johannes Kepler. He was obsessed with harmony. He believed the universe was built on geometric perfection. He spent years trying to fit the planets into these nested spheres, these perfect circles. And he failed, but the data he was using, that was the key. It was a treasure. It belonged to Tycho Brahe, this Danish nobleman with a metal nose. He had a castle observatory. For decades, Brahe recorded the positions of the planets with an accuracy that was just unprecedented. It was meticulous work, a lifetime of measurements. And when he died, that priceless data set came to Kepler. Kepler trusted the numbers more than he trusted his own beautiful ideas. He decided to follow the data wherever it led. And it led him to abandon the circle completely. His first law was a shock. Planets move in ellipses with the sun at one focus. An ellipse is a flattened circle, like an oval. The sun isn't at the center. It's off to one side, and this simple, slightly lopsided shape, it finally matched what they were actually seeing. His second law was about speed. A planet doesn't travel at a constant pace. It speeds up when it's closer to the sun. It slows down when it's farther away. But the line from the sun to the planet, it sweeps out equal areas in equal times. You imagine a triangle connecting the sun to where the planet is. In 1 month, whether the planet is near or far, that triangle will always cover the same area. And that explained the uneven motion, the thing that had baffled astronomers for centuries. Then his third law. It provided a kind of cosmic harmony. It connected a planet's orbital period, its year, to its average distance from the Sun. The square of the period is proportional to the cube of the distance. It was a precise mathematical relationship, and it applied to every planet. Suddenly, the solar system wasn't just a collection of objects, it was a clockwork system. Governed by predictable rules, Kepler's laws transformed cosmology. It moved from philosophical speculation about perfect forms to a rigorous, predictive science. You could calculate where a planet would be on any future date. With stunning accuracy, this understanding of orbital dynamics, it was the essential foundation. It set the stage for the next giant, a man who would ask the simple, devastating question: if the planets move this way, what force is making them do it? Kepler's laws describe the motion. They got the paths exactly right, but they didn't say why. The planets moved in those ellipses, but nobody knew what was guiding them. Then the answer came. The story is about Isaac Newton sitting in a garden. He saw an apple fall, and in that, he saw something universal. He asked a question. If the apple falls to Earth, does Earth's pull reach all the way to the moon? And if it does, could that be what holds the moon in place, keeping it falling around the Earth instead of into it? That was the connection. It meant the physics of the sky and the physics of the ground were the same thing. No special substance up there. No angels pushing the planets. Just one force everywhere. He called it gravity, and he wrote a law for it. A simple, powerful mathematical rule. Every piece of matter attracts every other piece. The force depends on two things: the mass of the objects and the distance between them. Double the mass, you double the force, but double the distance and the force gets 4 times weaker. That's the inverse square law, a precise rule for attraction across space. With that one equation, he unified everything: the path of a cannonball, the orbit of the moon, the planets going around the sun. They were all the same principle. Kepler's elegant laws became a direct result of universal gravitation. The solar system was a clock, and gravity was the spring. This broke a boundary that had stood for 2,000 years. Since Aristotle, people thought the rules for Earth and the rules for the heavens were completely separate. Newton broke that division. The same force that brings down rain also moves the planets. The universe wasn't mystery and magic. It was order. You could predict it. You could calculate where a comet would be or how the tides would pull with just a pen and paper and this law. It was a moment of immense power. Humanity had found a key that seemed to unlock the mechanics of everything. And for centuries that Newtonian view held. It was tested, it was proven, but then we looked further. Beyond our solar system, to whole galaxies swirling, and a question would eventually come up. Does this beautiful, simple law of attraction hold true everywhere? Even on the largest scales, or would gravity itself, the force Newton defined, show us something new in the deep cosmos? Newton's gravity gave us a clockwork universe. But to really see how big it was, you had to know how fast its messages moved. For a long time, light seemed instant. A star shone and you saw it. A lamp was lit and the room was bright. It didn't seem to have a speed at all. Then in the late 1600s, a Danish astronomer, Ole Romer, was watching Jupiter's moons, and he saw the clock was off. He was watching the innermost moon, Io. It orbited Jupiter like a perfect little clock, eclipsed behind the planet every 42.5 hours. Romer timed these eclipses very carefully. He saw that when Earth and Jupiter were far apart, on opposite sides of the Sun, the eclipses came a little late. And when they were closer together, the eclipses came a little early. The difference was small, about 22 minutes at most, but it was consistent. The error grew as the planets moved apart and shrank as they came together. Romer realized the only answer was that light had a speed, a finite speed. When Earth was farther from Jupiter, the light telling us Io was eclipsed had to travel farther. That extra distance took extra time. The eclipse wasn't late. We were just seeing it late. In 1676, he announced it. Light didn't arrive instantly. It traveled, and he even estimated its speed. About 220,000 kilometers per second. That's about 25% slower than the real value. But for a first measurement of something thought to be infinitely fast, it was staggering. The meaning was deep. It meant looking into space wasn't looking at the present, it was looking into the past. When you see Jupiter, you see it not as it is now, but as it was about 45 minutes ago, the time its light takes to reach us. That introduced look-back time. Light became a historian. Every beam carries a story from a moment already gone. This finite speed changed our sense of scale. Before, the universe could have been any size. Now, distance and time were tied by a universal constant. To measure how far something is, you could measure how long its light took to get here. That idea became the bedrock of modern cosmology. It meant when we finally turned telescopes to the stars, we weren't just mapping lights, we were opening a history book. The deeper we looked, the further back in time we saw. And that ability to peer into the past would eventually lead to the most shocking discovery: that the universe itself has a history, a beginning, and that its very fabric is stretching in a way no one could have predicted. Newton's laws and the finite speed of light gave us a universe of rules, measured by time. But the most basic question was still there. How far away are the stars? Astronomers had known for centuries the planets moved in our solar system. They could calculate those distances with geometry, using the sun as a baseline. But the stars were fixed. They didn't seem to move relative to each other. They were just points of light on a dark dome. Were they nearby lanterns, or were they other suns impossibly far away? That debate was ancient. To settle it, you needed a measurement. You needed to see a star shift its position just a tiny bit as Earth moved in its orbit. That shift is called parallax. It's the same effect when you hold up a finger and look with one eye closed, then the other. Your finger seems to jump against the background. If the stars were close, then as Earth traveled from one side of its orbit to the other, a nearby star should appear to jump against the backdrop of more distant stars. But for 2,000 years, no one could measure that jump. The instruments weren't precise enough. Or maybe the stars were just too far away. It became a test. If you could find stellar parallax, you proved Earth orbited the Sun. And you proved the stars were other suns at vast distances. If you couldn't find it, maybe the old ideas were right. The pressure was immense. Then in the 1830s, a German astronomer named Friedrich Bessel took on the challenge. He didn't choose a bright, famous star. He chose a faint, unremarkable one in the constellation Cygnus, called 61 Cygni. He chose it because it had a large proper motion, meaning it seemed to drift across the sky faster than other stars. That hinted it might be closer. For over a year, Bessel meticulously measured the position of this faint star against two even fainter stars behind it. Night after night, he tracked the tiniest possible wobble. And in 1838, he announced it. He had measured the parallax. The star shifted by an almost unimaginably small angle. 0.314 arcseconds. An arcsecond is 1/3600th of a degree. It's the width of a coin seen from 2 miles away. That's the shift Bessel measured. From that tiny angle and the known width of Earth's orbit, he calculated the distance. 61 Cygni was about 10.3 light-years away. A number so large it was difficult to grasp. The light from that star, traveling at that incredible speed, took over 10 years to reach his telescope. In that moment, the universe exploded in size. The stars were not decorations on a sphere. They were other suns scattered across a void of staggering scale. Our solar system was a tiny neighborhood in an immense city of stars. Bessel's measurement did more than give us a number. It gave us a ladder, the first rung on the cosmic distance ladder. Once you know the distance to one star by parallax, you can calibrate other methods to reach further. It was the first step out of our solar backyard and into the galactic frontier. But this vast new scale brought a new, deeper mystery. If stars are that far apart, how many are there, and how are they arranged? Is our sun just one among countless others in a shapeless cloud? Or is there a structure, a shape, to this immense city of suns? The quest to map our place in this new ocean of space was just beginning. The universe was full of stars, but we could only see it with our eyes, and then there was William Herschel. He was a musician who became an astronomer. He's the one who found the planet Uranus, but his biggest discovery started with a simple question about sunlight. He used a prism to break light into a rainbow, and he knew each color had a different warmth. So he put thermometers in each band of color. He had another thermometer off to the side, just sitting there. And as he went from violet to red, the temperature went up. That made sense. But then he moved a thermometer just past the red, where there wasn't any light to see. And that thermometer got the hottest. There was invisible light there, carrying heat. He called it calorific rays. We call it infrared. That changed everything. Light wasn't just what we could see. The spectrum went beyond into the invisible. The universe was talking in wavelengths our eyes could never catch. That one discovery opened a door. It meant everything, every object, every star, every planet, even our own bodies, was always giving off this invisible light. It was a form of communication we'd been deaf to. Herschel gave us a new sense, and that led to non-optical astronomy. If we could build tools to detect these other wavelengths, we could see a hidden universe. Clouds of dust in space that block visible light become clear in infrared. The warm centers of newborn stars, still wrapped in dust, could finally be seen. The cold, dark places between stars where new worlds might form could be studied. We realized the cosmos was more vibrant, more detailed than the silent show we saw at night. It was alive with invisible energy, and that raised a deeper question. If so much of the universe's conversation was happening in channels we couldn't naturally hear, what else were we missing? What was the universe itself made of? We could see the hidden structures now, but we still had to figure out the ingredients. The quest to understand what everything is made of, from the stars above to the ground under our feet, that was the next frontier. The light from a star looks like a single point, but if you spread it out, the story changes. In the 1850s, Robert Bunsen and Gustav Kirchhoff started working together. Bunsen had his burner, a clean flame. Kirchhoff used a prism to look at the light from that flame. They put different substances into the fire. Each one made a unique set of colored lines. Sodium gave 2 bright yellow lines, lithium was a crimson line, barium was green. Every element had its own fingerprint, a barcode written in light. You could identify something just by looking at its light. They turned this new tool, the spectroscope, toward the sun, and they found the same lines there. Those dark lines crossing the solar spectrum, first seen by Joseph von Fraunhofer, they weren't flaws. They were the fingerprints of hydrogen, sodium, iron, calcium. The sun wasn't made of some special celestial substance. It was the same ordinary matter we have here. That connection was profound. The same chemistry in a lab's candle flame also powered a star. The universe wasn't just ruled by the same laws like Newton showed. It was made of the same stuff. We were stardust long before the phrase. Astronomers then pointed their spectroscopes at the stars. And they found the same familiar fingerprints. Distant suns were also hydrogen and helium with traces of heavier elements. This cosmic chemistry united everything. The same periodic table applied everywhere. But this tool did more than identify ingredients. It revealed motion. By studying a slight shift in those spectral lines, you could measure if a star was moving toward you or away, and how fast. That would become a crucial clue. Yet spectroscopy also deepened a mystery. Out in the darkness were fuzzy patches of light, nebulae. Some, when analyzed, showed the fingerprint of glowing gas. But others showed a continuous spectrum like a star. Were these distant star clusters so far away their light blurred together? Or were they something else entirely, vast islands of stars separate from our own? The answer to that would force a confrontation with the true scale of the cosmos and our shockingly small place within it. The stars were suns, their light carried a chemical signature. But to map the universe, you needed more than that. You needed to know how far away they were. Parallax could only reach the closest stars. Beyond that, it was just a vast expanse. No landmarks. So how could you measure distances to those faint nebulae, or to those distant clusters that blurred into soft clouds of light? The answer didn't come from a famous astronomer. It came from a quiet woman at a desk, studying photographic plates. Henrietta Leavitt. She worked at the Harvard College Observatory in the early 1900s. She was a human computer, one of many women hired to catalog stars from photographs. Her task was to study variable stars, stars whose brightness changed over time. Among them were Cepheid variables named after Delta Cephei. Leavitt was given plates of the small Magellanic Cloud, a small satellite galaxy of our own. That detail was crucial, because all the stars in that cloud were, for all practical purposes, the same enormous distance from Earth. It's like looking at a distant forest. Some trees are taller, some shorter, but they're all roughly the same distance away. Any difference in how bright they appear is a real difference in their actual brightness. Not an illusion of distance. Leavitt measured the brightness of hundreds of Cepheids in this cloud. She noted their pulsation periods, the regular rhythm from dim to bright and back again. Some cycled in a few days, others took weeks, and she noticed a pattern. The longer the period, the brighter the star. A Cepheid that took 10 days to pulse was always brighter than one that took 5 days. A 20-day Cepheid was brighter still. A direct, predictable relationship. She had found a cosmic heartbeat with a consistent rule. The period told you the star's true, intrinsic luminosity. The period-luminosity relation. Its power was immediate. If you found a Cepheid variable anywhere in the sky, you could measure its pulsation period and know its true brightness. Then, by comparing that known brightness to how dim it appeared from Earth, you could calculate its distance. The faintness became a measure of the vastness. Leavitt had given astronomy its first reliable standard candle. A lighthouse in the cosmos whose wattage you could read from its blink. Suddenly, the measuring stick for the universe grew from a few hundred light-years to millions. This single tool, born from careful pattern recognition, became the key. It would unlock the greatest secret of our cosmic neighborhood. It would answer the question of our place among those spiral nebulae. Were they part of our own Milky Way, or were they entire galaxies of their own? So far away their light was a whisper from the deep past. The answer would redefine our address in the universe. Henrietta Leavitt's discovery gave us a ruler. Edwin Hubble used that ruler. He used it to measure the cosmos. In the 1920s, astronomers were having this big debate. Those faint, fuzzy spirals you'd see in telescopes, were they just clouds inside our own Milky Way, or were they something else? The key was finding a Cepheid variable star inside one of them. If you found one, you could measure the distance. And if the distance was enormous, far beyond the Milky Way, then the nebula wasn't part of us. It was its own island universe. Hubble had the most powerful telescope in the world, the 100-inch Hooker telescope on Mount Wilson. He pointed it at the Great Nebula in Andromeda. A beautiful spiral, a whirlpool of light. He searched the outer regions and he found it, a Cepheid variable. He measured its pulse, applied Leavitt's law, and got a distance. The number was staggering, nearly 1 million light-years away. That was far beyond any estimate for the size of the Milky Way. It couldn't be inside us. That faint smudge was an entire galaxy, a colossal city of maybe hundreds of billions of stars, separate from our own. With that one measurement, the universe expanded. In a single leap, our Milky Way wasn't the universe anymore. It was just one galaxy among countless others. The cosmos wasn't a single island, it was an archipelago. An ocean of space filled with island universes. The scale was almost impossible to grasp. Every faint patch of light they'd catalogued. Every spiral, every elliptical nebula. Probably another galaxy. The known universe went from 1 to billions, just like that. It was a profound demotion for our home. We went from living in the entire cosmos to living in a suburb. One suburb of one galaxy among billions, the ultimate Copernican shift. We weren't at the center of the solar system. We weren't at the center of the galaxy. And now our galaxy wasn't even special. It was ordinary, a single leaf in an infinite forest. But Hubble wasn't finished. He had the distances to these galaxies. And he had another piece of data, from the spectral lines in their light. That data held a secret, a pattern, so strange and so consistent it would point to something even more fundamental. Something that would change our understanding of time itself. Hubble had the distances, and he had the spectra from the galaxies, and that light told another story. A more startling one, when he looked at the spectral lines, those fingerprints for hydrogen, for calcium. He saw they were all shifted toward red. A redshift, and this was a known thing, like the Doppler effect with sound. A siren coming toward you sounds higher. Going away, it sounds lower. Light works the same. Something moving away stretches the light, reddens it. Something coming toward you compresses it, blues it. And every galaxy he looked at, almost everyone, showed this redshift. They were all moving away, all racing away from us. That was strange on its own, but then he plotted it. He put distance on one axis, velocity from the redshift on the other. And the points didn't scatter. They lined up. They lined up almost perfectly. The farther the galaxy, the faster it was going. A galaxy twice as far was moving twice as fast. 10 times as far, 10 times as fast. That was Hubble's law. A clean line, a linear relationship, and that changed everything. Because it meant the universe wasn't just big. It wasn't just full of galaxies, it was growing, actively growing, and uniformly. Space itself was stretching, carrying the galaxies apart, like raisins in rising dough. In a loaf of bread, every raisin sees all the others moving away, and the farther apart two raisins are, the more dough expands between them, so the faster they separate. There was no special center. No galaxy at the middle. From anywhere you'd see the same thing. Everything rushing away, so the universe wasn't static. It wasn't eternal and unchanging like people thought. It was dynamic. It had a history, and if you rewound it, if you played the film backward, all that space would collapse. The galaxies would crowd together. Density would rise. Temperature would rise to impossible levels. You'd be driven back, mathematically, to a single point. A point of infinite density. A beginning. The concept was staggering. It pointed to an origin. A moment when space and time and all matter and energy came into being. The Big Bang. Now, Hubble's data didn't prove the Big Bang, not yet, but it was the first clue. The crucial observational clue that the cosmos had a birthday. That the universe had a story, and the story had a first chapter. And if it had a beginning, then the next questions were overwhelming. What happened in that first moment? What set the expansion in motion, and maybe the most haunting one? What was there before the beginning of time? Hubble's law showed the universe expanding. But that expansion was happening in space. And space, what was it, really? Newton saw space as a fixed stage. An empty grid where things happened. But if that stage was stretching, what exactly was stretching? The answer didn't come from looking at stars. It came from a man imagining riding a beam of light. Albert Einstein began with two ideas. The laws of physics are the same for everyone, no matter how fast you move. And the speed of light is constant for everyone. That was special relativity. It led to strange things. Time slows down at high speed. Lengths shrink. Mass and energy are the same thing, but it didn't include gravity. Newton's gravity acted instantly across any distance. Relativity said nothing goes faster than light. So how could gravity work? Einstein spent a decade on that. His breakthrough was a shift in seeing. Gravity isn't a force pulling through space. It's a feature of space itself. End of time, he combined them into one fabric. Space-time and mass, he said, warps that fabric. Think of a stretched rubber sheet. Put a heavy ball in the middle. The sheet curves, makes a dip. Now roll a marble across it. The marble won't go straight. It'll curve toward the ball, maybe orbit. The marble isn't pulled by a force. It's just taking the straightest path through a curved landscape. That's gravity. The Earth orbits the Sun because the Sun's mass curves the spacetime around it. The Earth is just following that curve. That was general relativity. It redefined the most familiar force. It made predictions. One was that light would bend near a massive object. Because light travels through spacetime, and if spacetime is curved, light's path curves too. During a solar eclipse in 1919, astronomers measured starlight bending around the Sun. Just as Einstein said, another prediction was that time runs slower where gravity is stronger. A clock at sea level ticks slower than a clock on a mountain. We've measured that with atomic clocks, but the biggest implication was for extreme curvature. If you pack enough mass into a tiny space, the curvature becomes infinite. A hole in spacetime where not even light escapes. A black hole. General relativity gave us the math for black holes long before we had proof they existed. This theory didn't just fix Newton. It gave a new language for the cosmos. The universe wasn't objects in a void. It was a dynamic, flexible geometry. Mass tells spacetime how to curve. Curved spacetime tells mass how to move. That framework became essential for cosmology. It provided equations to describe an expanding universe, to model its beginning and its possible end. It forced a complete rethinking of cosmic geometry. The stage itself was alive, bending and stretching, and everything in it just moved along its curves. Einstein's equations described an expanding universe. The question was whether that initial state was real, whether there was any physical evidence for that hot, dense beginning. The evidence arrived as a kind of noise. In the early 1960s, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were using a large horn antenna. They were mapping radio waves from the galaxy, and they kept detecting this constant, faint signal, a microwave hiss. It came from every direction, all the time. Day and night, they checked everything. They cleaned pigeon droppings from the antenna. They recalibrated. The hiss stayed. It was a mystery, a universal static. Not far away at Princeton, a team led by Robert Dicke was building a detector. They were working from the Big Bang theory. Their reasoning was that if the universe started as a hot, dense fireball, it would have been filled with intense light. As the universe expanded and cooled, that light would stretch. Over billions of years, the wavelengths would stretch from visible light to infrared to microwaves. That glow should still be here, a faint, cool afterglow filling the cosmos. They called it the cosmic microwave background radiation. When Penzias and Wilson heard about that work, they understood. That annoying hiss wasn't an instrument flaw. It was the echo of the beginning, the leftover heat from the Big Bang, cooled by expansion to just 2.7 degrees above absolute zero. It was the oldest light, a snapshot from when the universe was about 380,000 years old. Before that moment, the universe was a hot, opaque plasma of particles and light. But as it cooled, protons and electrons combined into neutral hydrogen atoms. The fog cleared. Light could travel freely for the first time. That first flash of transparent light is what we see as the cosmic microwave background. It's the baby picture of the cosmos. The discovery was monumental. It was the smoking gun for the Big Bang model. It ended the scientific debate with the rival steady-state theory, which proposed a universe with no beginning, constantly creating new matter. The CMB showed the universe had a hot, dense origin. It was the same everywhere, confirming the universe is homogeneous on the largest scales. But then, with more sensitive instruments, scientists looked closer. They found tiny ripples in that smooth sea of microwaves. Minute temperature variations, just 1 part in 100,000. Those tiny imperfections were the seeds. The gravitational fingerprints of slightly denser regions. And from those seeds, drawn together by gravity over billions of years, grew everything: galaxies, clusters, the cosmic web. The CMB told us not only how the universe began, but why it looks the way it does now. It was the ultimate validation of looking back in time. You could point an antenna at the empty sky and hear the faint whisper of the universe's first breath. But if the beginning left a thermal echo, what about the other extreme? What happens when matter is subjected to the most intense gravitational pressures, collapsing beyond all limits? The theory predicted such objects. Finding them would require listening to the universe in a completely new way. The cosmic microwave background was this quiet, fading glow. But other lights out there weren't quiet at all. In the late 50s, radio telescopes were scanning the sky, and they picked up these strange, tight sources of radio waves. When astronomers looked with optical telescopes at those spots, they often saw what seemed like faint blue stars. They got catalogued as quasi-stellar radio sources. Quasars, they looked like stars, but they couldn't be stars. Their light told you that. When you broke their light into a spectrum, you saw the usual signatures of hydrogen and other elements, but they were shifted. Shifted way into the red, not just a small shift, a huge one. That meant they were racing away at a huge fraction of light speed. And Hubble's law said that put them at incredible distances. Billions of light years away. For something that far to still look as bright as a star in our sky, it had to be putting out a monstrous amount of energy. A single quasar can outshine an entire galaxy, a galaxy of hundreds of billions of stars, by 1,000 times, and it's doing that from a space not much bigger than our solar system. So what kind of engine could do that? The only possible power source was a supermassive black hole. A black hole with the mass of 1 billion suns, squeezed into a space smaller than Pluto's orbit. When huge amounts of gas and dust spiral into something like that, it doesn't happen quietly. The material forms this incredibly hot, spinning disk right outside the event horizon. Friction heats the disk up to millions of degrees, so it glows across all wavelengths. And intense magnetic fields can channel some of that incoming matter into 2 jets. Jets of particles shooting out at almost light speed for hundreds of thousands of light years. What we're seeing is the final scream of matter, just as it crosses that point of no return. Quasars aren't just distant oddities. They're time machines. Because light takes time to get here, the most distant quasars show us the universe when it was only a few 100 million years old. They show an era of chaos and building, when young galaxies were coming together, and their central black holes were feasting on all the gas around them. The fact that these behemoths existed so early was a deep puzzle. How did supermassive black holes get so big, so quickly? Their existence tells us the early universe was a place of extreme violence and rapid growth, where the seeds of today's giant galaxies were planted in a kind of frenzy. These brilliant beacons confirmed that black holes weren't just theoretical ideas or the endpoints of dead stars. They were active, dominant architects, shaping how galaxies evolved from the very start. Their discovery completed a picture of cosmic power, linking the most mysterious objects in Einstein's theory to the luminous engines that lit up the infant cosmos. Quasars revealed the engines, but the engines themselves were still hidden. Black holes were this perfect prediction from Einstein's general relativity. A place where so much mass gets squeezed into such a small point that space-time just curves in on itself completely. It creates a boundary, the event horizon. And nothing comes back from it, not a particle, not a single photon of light. By definition, they're invisible. So how do you prove something exists that you can never see? You look for the violence it inflicts on its surroundings. The first strong candidate came from the constellation Cygnus, an object called Cygnus X1. It was a powerful source of X-rays. Telescopes showed it was part of a binary system, a brilliant blue supergiant star orbiting something dark. Astronomers tracked the star's motion. From its wobble, they calculated the mass of its invisible companion. The number was staggering, at least 10 times the mass of our Sun. and all that mass was confined to a region smaller than a city. There's only one object in physics that can be that massive and that small: a black hole. The evidence was in the theft. The black hole's immense gravity was pulling a stream of gas from the surface of its companion star. That gas didn't fall straight in, it spiraled. It formed a superheated disk of plasma around the event horizon. Friction in that disk heated it to millions of degrees, causing it to glow fiercely in X-rays. We weren't seeing the black hole. We were seeing the last desperate light of matter being shredded and consumed. That was the confirmation, a silent monster revealed by the screams of its meal. Later, an even more direct proof arrived, not from light, but from ripples in spacetime itself. Gravitational waves. When two massive black holes spiral into each other, their merger sends tremors through the fabric of the cosmos. In 2015, the LIGO Observatory detected these waves for the first time. The signal matched exactly what Einstein's equations predicted for two black holes colliding. We heard the universe ring like a bell. With that, black holes moved from theoretical specters to observed reality. They are the ultimate endpoints of gravitational collapse, places where density becomes infinite, where our known laws of physics cease to function, a singularity. Yet for all their terrifying power, black holes are still just objects, made of normal matter compressed beyond recognition, and that fact led to a haunting realization. When we add up all the normal matter, all the stars, planets, gas, dust, even the black holes, it accounts for less than 5% of what must be out there. The universe, in its full composition, remained almost entirely in shadow. Black holes were gravity's final word on visible matter, but that was only a fraction of the story. In the 1930s, a Swiss astronomer, Fritz Zwicky, was looking at a galaxy cluster in Coma Berenices. He measured how fast the galaxies inside it were moving. And the result was shocking. They were moving far too fast. The visible mass, all the stars and gas, it just wasn't enough gravity to hold the cluster together. At those speeds, the whole thing should have flown apart long ago, but it was still there. Zwicky said there had to be unseen mass, dunkel materie, dark matter, providing that extra gravity. The idea was mostly ignored for decades. It seemed too strange. Then in the 1970s, Vera Rubin at the Carnegie Institution, she gave us undeniable evidence. She mapped the rotation of spiral galaxies very carefully. Newton and Einstein said stars on the outskirts, far from the bright center, should orbit more slowly. Like the outer planets in our solar system, they move slower. But Rubin's data showed something completely different. Stars at the edge of a spiral galaxy orbit just as fast as the ones near the center. The rotation curve was flat. That meant the galaxy's gravitational hold didn't weaken as you moved outward. So there had to be a huge amount of mass out there in the dark halo, mass we couldn't see, pulling on those outer stars. The math was inescapable. For every gram of glowing star stuff, there had to be about 5 times more of this invisible something. This wasn't a small anomaly. It was the dominant form of matter in the universe. Dark matter isn't black holes. It isn't cold gas, we know that. It doesn't absorb or emit or reflect light in any way we can detect. It interacts only through gravity. It's a ghostly scaffold, and we see its fingerprints everywhere. It bends light from distant galaxies' gravitational lensing, distorting their shapes. It governs how galaxies cluster together into a vast cosmic web. Without dark matter's gravitational wells, ordinary matter would never have clumped together fast enough after the Big Bang to form the galaxies we see. Stars, planets, us, we're just the visible froth on a deep, dark ocean. That realization was a profound shock to our cosmic inventory. All the stars in all the galaxies, every planet, every speck of dust, every black hole, it all adds up to less than 5% of the universe. Dark matter makes up about 27%. So what is it? The leading idea is it's a new kind of elementary particle, one that rarely interacts with the normal matter we're made of. Experiments deep underground are trying to catch a fleeting interaction. Particle colliders are trying to create it. So far, it stays elusive, but its gravitational signature is unmistakable. We live in a universe dominated by a substance we cannot see, touch, or yet understand. It shapes everything, yet reveals itself only by the pull it exerts on the lights we can see. And if that wasn't strange enough, astronomers soon found that even this dark matter scaffolding wasn't the whole story. There was another, even more dominant and enigmatic component at work. One that wasn't pulling the universe together, but actively tearing it apart. Dark matter was the hidden structure, but its pull wasn't the only force. In the late 90s, two separate teams of astronomers were trying to measure how the universe's expansion rate had changed over time. They used a specific cosmic explosion as a standard candle, a Type 1a supernova. These are thermonuclear blasts of white dwarf stars. They always explode with almost the same peak brightness. So if you measure how bright they appear, you can calculate their distance very precisely. And if you measure their redshift, you know how fast they were moving when the light left them. The goal was to see how much the expansion had slowed over billions of years. Gravity, from all the matter, dark and visible, should have been putting on the brakes. They looked at supernova in extremely distant galaxies. Light from those explosions had been traveling for billions of years. They were seeing the expansion rate in the universe's youth. And when they compared that ancient rate to the modern one, they expected to see a slowdown, a deceleration. What they found was the opposite. The distant supernova were fainter than they should have been. That meant they were farther away than the standard model predicted. For them to be that far, the universe must have been expanding more slowly in the past than it is today. The expansion wasn't slowing down, it was speeding up. The acceleration was increasing. That was a shock. It reverberated through cosmology. It was like throwing a ball into the air, and instead of slowing down and falling back, it shot away faster and faster into the sky. Something was overpowering the collective gravitational pull of all the galaxies, all the clusters, all the dark matter. That something got a name: dark energy. It's not a substance like matter. It seems to be a property of empty space itself, a repulsive energy inherent to the vacuum. And as the universe expands, more space comes into existence. Which means more of this repulsive energy. It creates a feedback loop. It drives the expansion ever faster. The numbers are staggering. Dark energy makes up about 68% of the total mass energy content of the cosmos. Dark matter is about 27%. And all the normal matter, everything we see and are made of, is less than 5%. The universe is dominated by two profound mysteries we don't understand. One that pulls and one that pushes. This discovery completely rewrote the predicted fate of the cosmos. Before, the future was a choice. Either a big crunch, where gravity eventually wins and pulls everything back, or a slow, cold expansion into darkness. Now, with accelerating expansion, the future looks different. Distant galaxies will eventually be carried away so fast that their light can never reach us. The cosmic horizon will shrink. In a far future, an observer in a galaxy like ours will look out and see only a local group of galaxies, bound together by gravity, in an otherwise empty, black void. All evidence of the larger universe, of the Big Bang, of the cosmic microwave background, will have vanished over the cosmological horizon. It's a lonely, quiet ending. The discovery of dark energy was a humbling reminder. Just when we thought we were mapping the cosmos, it revealed a deeper, more dominant layer of physics we hadn't anticipated. It forced us to confront a simple, unsettling truth. We understand only a tiny fraction of what the universe is made of. The universe was always mysterious and full of possibility. For a long time, we didn't know if other stars had planets. Was Earth a rare accident or something that happened all the time? That answer finally came in the 1990s. It came from a wobble. Astronomers Mitchell Mayer and Didier Queloz were looking at a star, 51 Pegasi. They used a method, the radial velocity technique. They measured the star's light with incredible precision, and they saw a shift, a rhythmic shift, blue shift then red shift. That tiny wobble meant something was pulling on the star. An unseen companion. In 1995, they announced it. The data showed a planet, but this planet wasn't like anything here. 51 Pegasi b was a giant. Half the mass of Jupiter, and it orbited extremely close to its star. A full year there was just 4 Earth days, a hot Jupiter. Our theories said that shouldn't be possible. That close to a star, the discovery was a shock. It proved planets could exist around other suns, but it also showed they could be completely different from what we knew. That one finding changed everything. It opened the floodgates. Then came the Kepler Space Telescope, launched in 2009. It used the transit method. It stared at one patch of sky. It watched the brightness of over 100,000 stars, looking for that periodic dimming when a planet crosses in front. Kepler was a statistical machine. It didn't just find individual planets, it proved they were everywhere. The data told us planets outnumber stars in our galaxy, that most stars have at least one. And that small, rocky worlds in that habitable zone where liquid water could exist, those are common. The variety was staggering. Super-Earths, planets bigger than ours but smaller than Neptune. Mini-Neptunes with thick atmospheres, planets orbiting 2 stars like in the movies, worlds so close to their star the surface is molten, others drifting alone in the dark. Our own solar system, with its neat order, rocky planets inside, gas giants outside started to look like just one arrangement, one possibility among countless others. We weren't the blueprint. We were a single example in a gallery of infinite design. This shift did more than add to a list. It changed the search for life. From a philosophical question to a practical one, a statistical endeavor. If rocky planets in temperate zones are common, then the ingredients for life are scattered everywhere. All across the galaxy, the next step is to look into the atmospheres of these distant worlds, to search for chemical signatures, biosignatures like oxygen or methane. Hints of biological processes. We're not asking anymore if other Earths exist. We're starting to ask which ones might be inhabited. That changes our own perspective completely. We are not a singular, lonely oasis. We are likely one voice. In a chorus we are only just learning how to hear. Einstein's equations said spacetime could ripple. But for 100 years that was just math. Then, September 14, 2015, 2 huge machines, one in Louisiana, one in Washington, part of LIGO, picked up a signal. A tiny chirp. A vibration so small it's hard to believe. It changed a 4-kilometer laser beam by 1/10,000th the width of a proton. That faint tremor was a gravitational wave. A ripple from 2 black holes colliding, each about 30 times the mass of the Sun, over 1 billion light-years away. In their final moments, spiraling in at nearly light speed, merging into one, they shook the fabric of the universe. That tremor traveled for 1 billion years, then it reached Earth. We heard the cosmos. For the first time, we observed an event not with light, but with the distortion of spacetime itself. A new sense, a new astronomy. Before this, we studied the universe by collecting light. Radio waves, X-rays, all electromagnetic radiation. But gravitational waves are different. They're not radiation. They're the stretching and squeezing of space itself, from colossal, accelerating masses. Most cosmic events make both light and gravitational waves. But the waves come through clean, unaffected by dust or gas. They give us a direct view into the heart of the most violent processes. That first detection confirmed a century-old prediction. Stunning precision, but more importantly, it opened a window onto a dark universe. Think of it like this. All of human history, we've been watching a silent movie of the cosmos. We could see the explosions, the swirling galaxies, the shining stars. With gravitational waves, we turned on the sound. Now we can hear the impacts. The mergers, the collisions, we're listening to the universe's soundtrack. And what we're hearing is a symphony of catastrophe. Black holes colliding. Neutron stars merging incredibly dense stellar corpses. Events that often make little to no light, hidden behind debris or in the pure darkness of empty space. But their gravitational roar is unmistakable. Since that first detection, LIGO and its European counterpart Virgo have heard dozens of these events. Each one teaches us about extreme gravity, how matter behaves under pressures and densities impossible on Earth. They tell us how often black holes pair up and merge, clues about the life cycles of stars. The crowded dynamics of galactic cores. One event, though, August 2017, a landmark. The detectors heard the signal of two neutron stars merging. And then, just seconds later, space telescopes saw a flash of light, a gamma-ray burst. This multi-messenger event was like a phone call with a video attachment. The gravitational waves told us what happened, the merger. The light told us what it made, a brilliant kilonova explosion. It forged heavy elements, gold, platinum, scattering them into space. We literally heard and saw the creation of precious metals. That connection showed how gravitational wave astronomy can work with traditional methods. To tell a complete story, this new sense is still young, but it's already reshaping our understanding. It lets us probe the moment of merger itself, testing general relativity in its most extreme regime. It may one day let us hear the faint rumble from the Big Bang, a primordial gravitational wave background. We've moved from being silent observers of a visual cosmos to listeners. In a universe that rings and trembles with the motion of its most massive objects, every new chirp from the dark is a message from a place we could never otherwise see. A direct testament that space isn't a static stage. It's a dynamic, living fabric, carrying the echoes of every cataclysm. Gravitational waves let us hear collisions out in the cosmos. But the deepest thing about the Big Bang isn't sound, it's geometry. The universe looks incredibly smooth and flat on the largest scales. The cosmic microwave background is almost perfectly uniform. Two regions on opposite sides of the sky, they could never have been in contact, not if light has a finite speed. And yet they have exactly the same temperature. How is that possible? In the early 80s, a physicist named Alan Guth proposed an answer. A fraction of a second after the beginning, the universe went through a period of hyper-fast expansion. He called it cosmic inflation. In this idea, a tiny patch of space, smaller than a proton, was filled with a strange, repulsive energy. That energy caused the patch to inflate exponentially, doubling in size over and over, faster than light could keep up. In less than a blink, that subatomic speck became larger than our entire observable universe. This sudden, violent stretching smoothed everything out. It ironed out any wrinkles, any temperature differences. It made the cosmos uniform, and it stretched the geometry of space itself to near perfect flatness. Inflation solved several major puzzles at once, but the theory had a side effect, a fascinating one, some might say unsettling. What if inflation doesn't start and stop just once? What if, in some regions, it stops? It creates a bubble universe like our own, but in other regions it goes on forever. The mathematics suggest this could happen. If the inflationary field is like a landscape with valleys, our universe formed when the field rolled into one valley. It released its energy as the heat of the Big Bang. But other parts of the field might still be rolling, or they might have rolled into different valleys. Each valley could represent a separate bubble universe, with its own laws of physics, its own constants, its own version of reality. In this picture, our entire cosmos, with its hundreds of billions of galaxies stretching over 93 billion light-years, is just one bubble. In a frothing, infinite sea of other bubbles, a multiverse. This isn't a parallel universe in the science fiction sense, with another version of you. These bubble universes are entirely separate. The space between them is still inflating, expanding at such a rate that no signal, no light, no particle could ever cross the gap. They are forever beyond our cosmic horizon. We are causally disconnected. We can never observe them, Never communicate with them. Never prove they exist. So why take the idea seriously? Because it emerges naturally from our best theories of the early universe. It's a prediction, not just speculation. And it reframes the deepest questions we have. Why are the laws of physics so finely tuned to allow for stars, planets, and life? In a multiverse, the answer could be a form of cosmic selection. If there are an infinite number of universes, each with random physical constants, then of course we find ourselves in one of the rare bubbles where the numbers work. We are here because this is a universe that could produce observers. It's a shift in perspective, humbling and expansive. It suggests the ultimate frontiers of reality may lie forever beyond our reach. Not because of technological limits, but because of the fundamental structure of spacetime itself. Our universe, for all its majesty, might be a single page in an infinite book, most of which we will never read. This idea forces a confrontation with the very nature of scientific inquiry. How do we explore a reality whose full extent is, by definition, unobservable? The answer may lie not in looking farther out, but in looking deeper within, to the fundamental laws that gave rise to this astonishing possibility in the first place. The multiverse pushes reality past what we can see. But sometimes the universe gives you something to look at. For 100 years, black holes were just math in Einstein's theory. We saw the effects, the X-rays from things falling in, the gravitational ripples when they crashed together. We knew they were there, but we'd never seen the main thing. The event horizon, that line you don't come back from, that changed in April of 2019. The Event Horizon Telescope. It wasn't one telescope. It was 8 radio observatories all over the world. In the deserts of Chile, on the volcanoes in Hawaii, on the ice at the South Pole. Linking them together made a virtual telescope the size of the whole planet. An eye as big as Earth. They pointed that eye at 2 places for years. The supermassive black hole in our own galaxy's center, Sagittarius A. And then a real monster. The supermassive black hole in the galaxy Messier 87. 55 million light-years away. A mass of 6.5 billion suns. The data was enormous. Petabytes of it, hundreds of hard drives. It took 2 years of supercomputer work to put the picture together. And then there it was. A fuzzy, orange ring. A bright, uneven donut of light around a dark center. That dark center wasn't the black hole. It was the shadow of the event horizon, the light bending so much around it that it left a void. The ring was the photon sphere. Light from gas swirling almost at light speed, superheated, bent and lensed by the huge gravity before some of it got to us. The picture matched what Einstein's math said a black hole should look like. The size, the shape, the lopsidedness from its spinning, it was all there. This wasn't just a photo, it was a test of general relativity in the most extreme gravity we could find. The theory passed, completely, the curved geometry of space-time. The bending of light, the event horizon itself, it wasn't just equations anymore, it was a photograph, proof that these things are real, and they act exactly like the 100-year-old theory said they would. Capturing M87 was a human triumph, a global one. It gave a picture to some of physics' deepest ideas. It closed a loop, a century of prediction and then proof. From Newton's apple to Einstein's curves, from a theoretical point to a glowing ring in space. These discoveries, from the Earth moving to a black hole's shadow, they mark our modern understanding. They tell a story of humility and wonder. How we've pieced together our place, bit by bit, in a cosmos much stranger and grander than we imagined, and that story isn't finished. That black hole image isn't an end, it's a start, a new way to see. It makes you ask the next question: what's on the other side of that shadow, that photograph of M87, that shadow? It's an end, a final line, but it's also a mirror. It reflects our own path. We began with a simple idea, that Earth was the center of everything, and over centuries, through these 20 discoveries, we took that idea apart. Piece by piece, we moved the Earth, we gave it an orbit, We found the force that keeps it there. We learned light has a speed, so every look is a look back in time. We measured the distance to the stars. We saw our sun is one of countless billions. We saw those billions form galaxies, and those galaxies all rushing away from each other. An expanding universe, an accelerating one. We heard the echo of its violent birth. We found the invisible scaffolding, dark matter, the even more mysterious push, dark energy. We learned planets are common. Black holes are real. The fabric of space can ripple. We've been evicted from the center over and over. The shift is monumental. From a small, static stage with Earth at the center, to an immense, dynamic, accelerating cosmos, we're a fleeting presence on a speck of dust. This isn't just a change in facts. It's a change in feeling, a profound humility. We've learned the universe is predictable, governed by elegant mathematics, and yet it's full of shocking, unpredictable surprises. Every time we thought we had the complete picture, the cosmos showed us a new layer of mystery. Newton's clockwork gave way to Einstein's curved space. The steady-state universe gave way to the Big Bang. The search for planets gave us hot Jupiters where we expected none. And just when we mapped the galaxies, we found that 95% of the cosmos is made of stuff we cannot see. Stuff we don't yet understand. Our understanding is still incomplete. We have names for the unknowns: dark matter, dark energy, the singularity inside a black hole. The conditions of the very first moment. But names aren't explanations, they're placeholders for our ignorance. Each answer we've found has opened two new, deeper questions. Finding the cosmic microwave background confirmed the Big Bang, but then we had to ask what came before. Discovering the accelerating expansion gave us dark energy, but now we must ask what it truly is. Is it a constant energy of the vacuum, or something that changes over time? The fate of the entire cosmos depends on the answer. This is exploration. The frontier doesn't disappear as we advance, it transforms. The great unknowns waiting for us are perhaps even more baffling than the ones we've already solved. What is the true nature of dark matter? Is it a particle or something stranger? Why does dark energy have the value it does? What happens to information that falls into a black hole? Are we truly alone, or is life a common cosmic phenomenon? And on the grandest scale, is our universe just one bubble in an infinite, unobservable multiverse? These aren't just puzzles for scientists. They're questions for all of us. They define the reality we inhabit. This journey, from an Earth-centered cosmos to an accelerating, multiverse-implying reality, is perhaps the greatest story ever told. It's a story of human curiosity, of looking up at the night sky and refusing to accept easy answers, of building better tools, asking sharper questions, and having the courage to follow the evidence. Even when it leads to a universe vastly stranger and more wonderful than we ever dreamed. The discoveries of the past have brought us to the edge of a new wilderness. The next chapter is being written right now, by telescopes peering at the atmospheres of distant worlds, by detectors listening for the faint whisper of dark matter, by theorists grappling with the quantum nature of gravity. The map is far from finished. In fact, the most exciting parts might still be blank, waiting for the next observation, the next insight, the next great discovery that will once again completely change our understanding of space. Our understanding of the cosmos today would look like magic to someone 100 years ago. That change comes from a simple human act, looking at the sky and asking why. It's the story of Kepler, who trusted messy data over perfect circles, of Leavitt, who saw a cosmic heartbeat in the flicker of stars, of Penzias and Wilson, who chased a hiss until it showed the universe's first light. Each breakthrough started with a question, a willingness to let the evidence, however strange, rewrite the story. We went from a small, Earth-centered stage to an accelerating cosmos of unimaginable scale, a cosmos driven by dark energy. We've seen the shadow of a black hole. We've heard ripples from colliding neutron stars. These 20 revelations are more than facts. They're chapters in humanity's greatest adventure. an adventure that doesn't need a rocket ship. It happens when we point a telescope, or run a simulation, or just look up on a clear night and wonder. The quest to understand the stars redefines our place again and again. It teaches humility and it fills us with awe, so keep observing, keep questioning. The next discovery is out there, waiting for a curious mind. We want to hear from you. Which one of these discoveries changed your perspective? Let us know in the comments. And if you want to join us for more journeys into the mysteries of space, be sure to subscribe.